Okay, this will be our second video where we look at, again, the exception for doing integration by parts and letting u be the part that actually differentiates to 0. And actually, we can think of it more as a way to integrate a natural log function, because when you have a natural log function, there are only two ways that you can perform that integration. Number one would be with a u substitution, and number two would be with a integration by parts. So let me throw a couple of these up here and we'll see what we can do with them. Let me start by looking at, for example, the integral of 1 divided by, x, natural log of x, with respect to x. And so as soon as you see that you have a natural log, again, you only have two choices in this. The first is, can you do a u substitution? In a u substitution, what's important is we're going to let u be the natural log of x piece. And if that's the u, then the u prime we need to go with that is exactly 1 over x. And I do have this here. If I can kind of schmooze this out and rewrite this as 1 over x times 1 over the natural log of x with respect to x, I see that this entire piece becomes my u prime. My u prime is not on the bottom, it's the whole 1 over x. But my u here is on the bottom, and so this becomes a 1 over u. Putting that together, I get u prime over u, and by definition, when I integrate that, I'm going to get the natural log of the absolute value of u plus c. So putting back in my u, this is going to give me the natural log of the absolute value of the natural log of x, all plus c. So here again, we can see that what we have going on here is a u substitution. Another example here for a natural log function, something like, I don't know, the integral of the natural log of x quantity squared divided by x with respect to x. And again, what's important is if I see a natural log that I need to integrate, I'm going to try a u substitution, and I need that u prime. If I can't do that, that forces me to go in and do an integration by parts. So let's see if we can do that u substitution. Again, if we're going to do a u substitution, we're going to let u be the natural log of x. That's always our choice. Then the u prime will become 1 over x. So again, if I were to kind of schmooze this thing apart, I see that I can rewrite this as 1 over x times the natural log of x quantity squared with respect to x. And then remember that this entire thing here would be your u prime, and this looks like a u squared. And of course, when you integrate the u prime times u squared, you're going to get 1/3 u cubed plus c. And so putting back in my u, this is going to give me 1/3 times the natural log of x quantity cubed, all plus c. So again, nothing more than a simple u substitution. Okay, in this next example, it's going to look very similar to the one I just put up, but it is going to be quite different indeed. Let's try the integral of the natural log of x quantity squared with respect to x. And again, I see that I do have a natural log of x. So my first inclination would be to try to do a u substitution, but the problem here is that I do not have the u prime that I need. I don't have the 1 over x, and there's no way to get it in here. That means that I'm going to have to do an integration by parts. Now, in an integration by parts, we're going to pick that u completely differently. Because remember, in an integration by parts, I am redefining this entire integral. So the u that I'm going to pick here is not the thing that's being raised to a. It will actually be the entire natural log piece. That is the natural log of x quantity squared. That leaves the remaining part of this to be my dv. So dv will simply be dx. Again, if we look back to the integral we started with, we have now defined this integral as u dv. Now look at how that choice of u differs from what we did in a u substitution. In a u substitution with a natural log of x, I am only going to pick the u to be the natural log of x, no matter what power it's being raised to. So even if it were a natural log of x cubed, I'm only going to pick the u to be the natural log of x. In a integration by parts, I need it to be the entire natural log piece, including the power that's being put on it, so that I can define the whole thing to be that u. So it's a different way of defining those things. Well, now that we have our u and our dv defined, let's find the rest of the parts we need. We're going to need du, and remember du dx is nothing more than u prime, and this looks like a chain rule. So the 2 is going to come down in front. We're then going to take that natural log of x and raise it to the 2 minus 1, or first power, times the derivative of what's inside, which is 1 over x. And then, of course, you might want to clean that up a little bit and go ahead and solve that for du by multiplying both sides by dx, and I get that du is equal to, and I might write this as 2 over x times the natural log of x. That's 2 of the parts that we're going to need. We also need this other part here that we get from dv, that is, we're going to need v. V is going to be the integral of dv, so it's going to be the integral of dx, meaning v is simply equal to x. So we've got our pieces and our parts that we need. Let's go ahead and then define what we have in this integral. So started out with the integral of the natural log of x quantity squared dx, which again we defined as u dv, and by definition that's going to be equal to uv minus the integral of v du. So let's go ahead and put in all those pieces and parts. Okay, so this is equal to our u times our v, which is x times the natural log of x quantity squared, minus the integral of v du, which looks like x, times 2 divided by x natural log of x dx. And then, of course, I can clean that second one up. This looks like x, again, times the natural log of x quantity squared. Looks like these x's are going to cancel for me there. And I simply get minus the integral of 2 natural log of x dx. And so now I have this new integral that I need to look at, and let's go through the process on it. Again, I notice that I have a natural log of x. Only 2 ways to deal with a natural log of x. One is through a u substitution, which means I'd need a 1 over x. I don't have that. That means I'm going to need to do another integration by parts. Once again, I'm going to pick the u to be the entire natural log piece, and you can either attach the 2 with that, or you can leave it with the dx. The choice is yours. I'm just going to put it with my natural log of x. It really doesn't matter. The dv then will be everything else, which is the dx. And so based on these choices here, I can find the du by taking the derivative and multiplying both sides by dx, and the derivative of 2 natural log of x. Again, the x goes on the bottom, derivative of that on top, which is 1 times that 2, will give me a 2 over x dx. So I've got my u, I've got my du, and the only other thing I need is my v, and v will be the integral of dv, which is the integral of x. So my v here is x. And so once again, we're going to go through this process. And so let's come back up here and bring down this stuff that we have. So we started out with the integral of the natural log of x quantity squared dx, and we got down to where we had x times the natural log of x quantity squared minus our new integral. And so we need to make sure we're going to distribute that negative through, and remember what we're going to put in here is going to be uv minus the integral of v du. So we're going to take our u and multiply it times our v. That's going to give us 2x natural log of x minus the integral of v, which is x, times du, which is 2 divided by x dx. I kind of ran out of room on that there. But we can go ahead and clean this up and distribute that negative on through there. So I have x and then natural log of x quantity squared. That's going to give me a negative 2x natural log of x. The minus times the minus makes that a plus. I see that these two cancel, and I'm just looking at 2 times the integral, sorry about the color there, of dx. And so this finally gives me x natural log of x quantity squared minus 2x natural log of x plus 2x all plus c. And really, every time we pick a u, and this is the final answer, by the way, but every time we pick a u, and we use an integration by parts, the power on the u comes down by 1. Remember, we started here by picking u to be the natural log of x squared. And after we did the integration by parts the first time, we got down to this new integral, which had the natural log of x raised to a first power. And then we did integration by parts again to get rid of that. If we started out with a natural log of x cubed, we would have to go through the integration by parts 3 times, each time bringing it down by a power. Okay, the next 2 videos are going to deal with the second exception to our integration by parts.